Okay, welcome. What I'd like to do in this video is show you how you can use the heats of formation for compounds to predict a delta H for an overall reaction. The heats of formation of compounds are found in tables, and there are books and lists, and with my students I give them a reference packet that has a lot of these listed, and I have put into here a couple of sections of a data table, and I have circled the ones that I'm going to need as I go through this process. So what we do to get the delta H, remember enthalpy is really the enthalpy of the products minus enthalpy of the reactants. So what I'm going to do is I'm basically going to get the enthalpy, the heats of formation of my products, and subtract from that the heats of formation of my reactants. So products minus reactants. First thing you need to do is have a balanced equation, and if I were to balance this right now, I would start with, I'd say, I have 2 carbons here, so I'd put a 2 there. I have 6 hydrogens, so I'd put a 3 there, but the problem is then you'll notice you have 4 plus 3, I have 7 oxygens. I can't get 7 oxygens over here. So what I've always taught my students is when you have a situation like that, go back and double your hydrocarbon. So I have 4. I now have 12, so I'll put a 6 there. So now I have 8 plus 6. Now I have 14. That I can do by putting a 7. So now I have a balanced equation. And so now what I'm going to do is I'm going to take the heats of formation of my products and figure those out. So what I do is I say, all right, listen, this is CO2. So I come over here, and what is the heat of formation for carbon dioxide? It is negative 393.5. How many CO2s do I have? I have 4 of them. And I need to add that to my other product, and so that is water, and it is liquid. So what I do is I notice, in these tables they have the physical states at times. This is the liquid formation, so that's going to be negative 285.8 times I have 6 waters. Now I add all of these together, and I'm going to subtract from that then my reactants. But let me, as long as I have this up here, let me do this. Negative 393.5 times 4. I did this a moment ago, and if I did this correctly, I believe this is negative 1574. And I believe that this, if you go through the math here and take the negative 285.8 times 6, is negative 1714.8. Sorry. And so I'd add those together. And I'm going to subtract from that my reactants. Well, what are my reactants? Well, this is ethane. Ethane, if you look here, is negative 84.7. And I've got 2 ethanes. And then I want to add that to my other reactant. But one thing you need to recognize is the heat of formation of an element in its standard state, meaning its state at standard temperature and pressure. It's a normal state of just an element, which in this case is just oxygen, O2. That's its normal state. It's a gas, O2 at this thing, is always defined as 0. So 0 times 7 is, of course, 0. So I don't have to worry about that. That just goes away. So what this ends up being is you take all your compounds, put them together, subtract all your reactants, but for all of this you eliminate any elements that may occur. So actually I should have put this up here, negative 84.7 times 2. And what did I do? That came out to negative 169.4. Okay, so again, if I take the sum of these two numbers minus a negative, effectively then I'm adding it. And when I did this before, I got negative 3119.4, and that's going to be in kilojoules. These are typically kilojoules per mole. And so what ends up happening is I've now predicted the enthalpy change of my reaction to be negative 3119.4 kilojoules. And again, all I do is just add up the heats of formation of my products minus my reactants, and it's a very easy way, and it's another way to predict the enthalpy change for a reaction that I've not yet run. All right, thank you. Hope that helps.